Hi, my name is Zoe Baker, and today I'm going to present my poster on scaling multi-instance support vector machines for big data classification. So multi-instance learning is a type of learning where we consider data that falls into groups. So what does this mean? As an example, consider the problem of trying to collect data about a patient and diagnose them with a disease. So maybe they are in a hospital, and over the course of the time that they're there, you collect their vital signs, every few hours or days or whatever, and you end up with this collection of data about this patient. And then you want to use this collection of data about the patient to classify them with a disease. So you have multiple instances of data, but you want to label that entire bag of data as having this disease or not having that disease. So that's what multi-instance learning or classification is trying to do. So one tool that we can use to solve this multi-instance learning problem is called a support vector machine. And what support vector machines do is they basically try to draw a line in the data, or if there's more dimensions, we call that a hyperplane in the data that separates data into different classes. So one problem though with this traditional multi-instance SVM approach that a lot of people have tried to do is they use quadratic programming techniques to solve for this line, this hyperplane. And what happens is that quadratic programming is pretty slow and you can speed it up with heuristics, but these heuristics depend on having a low amount of support vectors. So what are support vectors? Support vectors are the points in the data that fall along that hyperplane that separates the data. Naturally, as you increase the amount of data in your data set, more points are going to fall on this hyperplane, and that means their methods are going to get slower. So our goal was to try to find or derive an alternate method that doesn't depend on the number of data points, doesn't depend on the number of support vectors, so that it scales well. And that's what we did. We derived a method using what's called the alternating direction method of multipliers. And if you look at our method's results in the graphs on my poster, our method scales better than most methods. However, there was still a computational bottleneck in our method, and that computational bottleneck was related to doing a least squares calculation with one of our updates for one of our variables. So we replaced that with an optimal line approximation. When we replaced this with an approximation creating an inexact method, this inexact method actually scaled linearly. So it basically did not, as we increased the number of features, the time it took for our method to run didn't increase at all. And finally, we also included a kernel extension so that our method would be able to handle separating data that's not linearly separable. So in future work, we'd like to make our exact version just as fast as an inexact version. But thank you, that was my research today.